So we're moving to glass fibers, and I think maybe you're more familiar with those. Plastic boats are typically made from glass fibers and unsaturated polyesters. There are lots of glass fiber composites out there simply because glass fiber is the lowest cost fibers out of those we've talked about so far, at least. So as the name implies, they are simply based on glass, and well, an important reason for using glass fibers is low cost. They're very different from carbon fibers in nature. So the structure of glass fiber is completely amorphous. It also means that the fibers are isotropic. In other words, you have the same properties in the axial direction of the fibers as you have in the transverse direction of the fibers, so that's important. Maybe I should actually start out by giving some data, because now you have the basis from the carbon fibers. So typically fiber diameter would be again around 10 micrometer. The density of glass fibers is something like 2.56 grams per cubic centimeters. Typical value for Young's modulus is 76 gigapascal, so we can put that in perspective. Most common form of carbon fibers have 250 gigapascal, steel has 200 gigapascal, but it's still reasonably good, 76 gigapascal. We know the polymers have something like 3 or 4 gigapascal in modulus in the glasses state. And maybe an interesting thing is to look then at strength values. So they are typically between 1.4 and up to 2.5 gigapascal. I will come back in a moment to why I give these numbers as a range. But I think this is a good starting point. The question then is, how do we process, how do we make glass fibers? And as you may imagine, well, it's based on silica, so silicon dioxide, and it means that we are basically starting with sand. Sand is the most important raw material. Of course, there are also other components, but this is an image of how the processing is done industrially. So you see that the sand is mixed with other components, and then this is molten, and it is fed into a large container. And perhaps the most interesting or the most important aspect is that the molten glass then is spun. So you basically have, well, maybe it helps if I turn this one the right way. So this is where you feed the different components. You have a mixer, you heat it, and then you basically use platinum bushings for the spinning of the fibers. So you have a, well, almost like what it looks like in the shower. You have, where the water comes out, you have solid glass fiber coming out. The difference is that these bushings need to be very hard, so they're platinum coated, and out comes the glass fibers, and there are many of them coming out at the same time, and then they are basically wound on a roll. It is important also to point out that there is a binder or a sizing agent used, sprayed on the fibers, and this is important because we need that in order for the fibers to have the characteristics that we want at a later stage. So this, in short, is what the preparation is like for glass fibers. I think the second thing that is important to know is this three-dimensional isotropic structure. So you can see silicon, and silicon is the black dots, oxygen are the open circles. So you see this is essentially a three-dimensional network of silicon dioxide or silica, and it's completely random, it's in space, so this is important. And we may then ask the question, how come that glass fibers have higher strength than window glass, for instance? And it's basically, the reason for that is pretty much that geometrical. So there's not a big difference in the composition of the glass in the glass fibers, but because of the geometry, you reduce the probability of having large defects. So the intrinsic strength of the fiber is vastly increased. The modulus is the same as it is in window glass. So this, I think, is important because it also means that since glass is a very brittle material, this surface smoothness of the fibers is very important. If we have damage of the fibers because of some mechanical handling problems, then the average strength of the fibers will be decreased. So if we compare it with carbon fibers, the basics for strength of glass fibers is slightly different. There is no orientation in the structure, but properties come from the small dimensions. Another very important thing to consider is if we look at the data for strength values of glass fibers, we can see some interesting features. If I look at the statistics of strength, and I just take the number of samples, and then I do this for different strength values. So this is 1, 2, 3, 4, and this is all in gigapascal. Then perhaps the weakest fibers are down here somewhere. Then the next sample has much lower strength. Well, let's say there are fewer specimens with high strength. Then we have something like this. And then the next, well, actually this is, I'm sort of getting unrealistic values here, but it doesn't matter to show my point here. So I need to shift my scale here to make it a little bit more reasonable. So yeah, so this should be something like 3 gigapascal. The point is simply that there's a lot of scattering in the data. So individual fibers may have extremely high strength, but then there are other fibers with low strength. And in the case of glass fiber, the reason is that you have surface defects on individual fibers because of handling most of the times. They're also susceptible to chemical attack. So if you have moisture present and you don't protect the surface, there will be defects forming on the surface. So this, I think, is very important. And another manifestation of this phenomenon is that if I change the length of my fibers, I will measure different values for strength. Because if I have a longer fiber, there is a larger probability that I will have a large defect. So we need to be aware of that all these strong fibers show substantial scatter in strength. So it means that if we just provide average values for strength, it doesn't give the whole picture, because first of all it could be a large scatter in data, and the other thing is that if we are interested in the strength for a longer fiber, we're going to get different values. So yes, to get strength values which are true material properties is a little bit difficult. So the numbers I quote in class, they are average numbers, and different types of fibers will show higher or lower scattering in data, but we will not go into details that much. All right, so let's then go into a different category of fibers, and those will be the polymer fibers. As I mentioned earlier on, I mean, we're all familiar with textile fibers, but they are typically designed to function in textiles. They don't have maximum strength. It's not required, and for that reason, polymer fibers are somewhat particular. And I would like then to start with polyethylene as an example. And polyethylene has a very simple repeat unit. But if we stretch the molecule so that we have aligned PE molecules, similar to, well, can be done with other polymers as well, then the interesting thing is that the theoretical value for the modulus could be something like 220 gigapascal. And the reason for that is that because of these small side groups, these are only hydrogen atoms, we can pack the polyethylene molecules very densely, and as a consequence, if we load it in the same direction as we have the molecules, we're loading high energy covalent bonds, and we can achieve very high values for modulus.